my topic today will be the data fusion method on satellite surface albedo products. This presentation is organized as follows. So, what is surface albedo and why is it so important? In this presentation, we will focus on the shortwave surface albedo. It's defined as the upward radiation to the downward radiation, the ratio at the Earth surfaces, and it's a very important factor in the surface radiation budget to control the surface shortwave radiation. And normally, in the previous research on the accuracy requirements, people say that surface albedo products on a global or regional scale should be within 0.02 or 0.03, the range. And actually, surface albedo can change dramatically as shown in those figures. Degradation, forest fire, and the clear cut. So it's a very important factor, indicator of the land cover change, land use change, and therefore it can be contribute to the radiative forcing, either the surface radiative forcing or POA radiative forcing. And people will already find that if the surface albedo change and introduce therefore the TOA albedo change will to the similar magnitude in terms of the radiative forcing to doubling of the carbon dioxide in the atmosphere. And it also can serve as the background information in retrieving some atmospheric variables, for example, the aerosol optic depth. There are already multiple long-term global satellite products, including MODIS, MISA, Global Albedo, GLASS, GLN2, from as early as 1980s. But some of the reports that generally the surface albedo products can satisfy the requirements globally, but some people say that on some regions there's still some accuracy issues. People find like 10 to 28% that equals to like 0.03 to 0.09 in accuracy. And inconsistency was also found between those products. They can be attributed to the algorithm difference, and some report that it's because of the band settings. And another problem of existing products is the data gaps. So it can be attributed to the sensor failure, algorithm limitation, and also cloud cover can be a very important problem because existing products, albedo products, rely on some kind of composite, temporal composite. If like 16-day composites can produce 20% gap, and if it reduced to 10-day composite, the gap doubled. Albedo data fusion is becoming a very hot topic recently. And what is the advantage of data fusing like multiple albedo products? It can generate a complete and continuous albedo products, and also consistent between like cross scales and platforms. And it can incorporate like different information, temporal, spatial, spectral, and angular informations. The resulting data fused albedo products can serve as the spatial and temporal constraints of the future albedo retrieving procedure. There are currently two major kinds of albedo data fusion methods. One is relying on it's called Bissell method, relying on the bidirectional reflectance distribution function as the proxy. Normally, people would use the MODIS BRDF as a database to transfer the information across scales. But the problem is that sometimes it's very difficult to find homogeneous pixels at different levels of spatial resolutions. The other kind of method is the data-driven method. People have done research using like long-term albedo products to derive to fill the gaps. But some problems also exist, like we need to evaluate the albedo uncertainty to carry out this kind of method. And also, bias will normally remain in the final product since they only rely on one product, one albedo product. In this presentation, I will introduce the data fusion method. Here, I use the multi-resolution tree, MRT, as the major method. The multi-resolution tree is actually a very simple idea, organizing the different albedo products at different resolutions as a tree structure. And this idea was proposed as early as 2002 for another product. The closest resolution data can serve as the root in a tree structure, and the finest resolution data product can serve as the leaf nodes in a structure. So there are major two kinds of procedures involved. The first one is the Kalman smoothing from the finest resolution to the closest resolution data to mainly fill the gaps. The second step is the smoothing to smooth from the closest resolution to the finest resolution. So they are organized as the Markov chain that indicate that the data structure in the tree level only is relevant to its immediate parent node and leaf node. What's the advantage of MRT? It can provide probability estimation since we use the Kalman filter. It can solve this change of support problem and very easy to understand and time efficient. This is the framework of how we carry out the MRT to fuse like multiple satellite products. Firstly, we collect multiple satellite products, original products, and also the ground measurements to do the accuracy evaluation to get the image-based uncertainty estimation. And secondly, because MRT relies on the anomaly, which means the bias should be removed before it can be carried out. And so we put the anomaly and the image-based uncertainty estimation into the Kalman filtering and the Kalman smoothing, and then update the accuracy estimation and to update the final products. In this study, we mainly use three albedo data set actually. The first one is the MISA, 1.1 kilometer every 16 days, and mode is 500 meters every 8 days, actually derived from 16-day composite. And the third one is not actually an operational product right now, but we use the surface reflectance derived from the LEADAPS tool at 30 meters every 8 days combined TM and ATM plus, and then transfer the surface reflectance to the surface albedo. This algorithm is actually becoming more and more mature. And we also collect the emerged flux size to evaluate the accuracy. We chose the north central United States as our study area. Mainly covers the cropland, grassland, shrubland, and some deciduous broadleaf forest. And here is some example of the comparison, intercomparison of the different satellite products at some emerged flux sites. And we can see generally the agrees, different products agrees well. But in terms of the spatial homogeneity of these sites, we can see that although MODIS products are very smooth and continuous, but still we can see scale difference. But Landsat matches the ground measurements quite well. But sometimes it suffers from like a residual cloud. For example, in the third figure, on day between 150 to 200. So that means still some problem with these data products. After removing those outliers, we can see generally Landsat data has albedo dataset has very good accuracy. Based on the site comparison, we use very limited site data ground measurements here. We derive the accuracy of Landsat data using a relative value here, because we want to use them to firstly get the first estimate of the error of each product. So after the data fusion, we can see in the right-hand side the estimated error greatly reduced from using the data fusion method. Here's some statistical comparison. In the left 4 figures, we can see that before MRT and after MRT, the differences between adjacent scales albedo products become smaller, and they are more consistent. And some people will say that data quality may play a factor in the data fusion, but we can see that if we divide the MODIS products from best quality and other qualities, we can see in the right figures not too much different, but slightly more larger RMSE can be seen from using bad quality data. But in terms of data quality, different products have different criteria in separating different qualities. So in our study, we will not use those data quality information. This is an example of using the MRT in the time series. We can see that in the first and third and the fifth columns, they are the original data products from MISA, MODIS, and Landsat. We can see that a lot of gaps, especially from MISA. Even we use a temporal composite to get a MISA albedo. And Landsat suffers from, for example, the ETM, Landsat 7 ETM plus data suffers from the scanline problems with a lot of gaps. We can see generally in the second, the fourth, and the sixth columns data after the data fusion method, we can see they're more complete and more consistent across different scales. Here's some statistical significance of using MRT. We can see generally the bias between products decreases, except for a few things. But if we look at the relative RMSE, they decreases quite significantly. For example, in left top between the MODIS and aggregate Landsat data, we can see around 18% difference. But after MRT, the relative RMSE reduced to within 13%. More importantly is that aggregated MODIS and MISA comparison, we can see that generally MISA has a lot of outliers, and after the data fusion, they become more consistent. Most of them are within 10%. To summarize this presentation, this is the first algorithm to our best knowledge that integrate multiple, at least 3 satellite albedo products at different spatial scales to build the more accurate albedo products. And the MRT method is proven to be very capable of generating the accurate albedo products, and it's very time efficient. And it also can be extended to other locations and time period. But some more investigations are needed to evaluate the existing albedo products to provide this kind of accuracy assessment in order for us to carry out the data fusion. Some references, and thank you.
thing is not clear to me. That your MRT seems to be quite effective. So can you hear? They seem to be quite effective. That has the function of filtering and smoothing. Now, what is filtered out? Is it the extreme values? And when these extreme values are filtered out, then you could not guarantee the bias that you estimated to be realistic.
That's a good question. Actually, the filter is actually a name here. What we do is actually filling the gaps, and the data, for example, the cloud problems will be this kind of problem will be solved in the smoothing steps, the second steps. So.
And how do you assess bias?
Bias is removed from using like some trend service techniques here. I did not mention it in the presentation.
I have one simple short question about the Landsat data. You have mentioned you use the Landsat data and generate very good results, match the ground measurement, right? And you said that the residual crowd has some influence on the data. But as we all know, Landsat data has suffered from thick crowd, especially for the tropical forest region. And how do you deal with the image with the thick crowd left in that region?
Thank you. This is a good question. Actually, Landsat data in this presentation, in this research, serve as the finest resolution data. If we really don't have a lot of data available, nobody can do a good job. In terms of estimating the surface albedo. If no data is available, so yeah, that's a good problem. But we'll use the temporal information, like cloud-free information, to interpolate the data to get a clear sky data. So that's our choice. Thank you.
Thank you, Dr. Let me call the second presenter,